Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today we have the privilege of having Rod Van Meter here with us. He is a professor at KO University. He's been visiting MSR all week, and today he's going to talk about internet-scale quantum repeater networks. So, Rod?
Thanks. So I have a tendency to kind of wander around as I talk, so I will be here, there, and everywhere. So we've had a very good week here at Microsoft Research. I think it's been a good learning experience for all of us, and I hope you guys have gotten something out of it as well. We've talked mostly this week about error correction, architecture, and compilers. So I want to kind of end the week on a little bit of a different topic. The other big area that I've been funded to do research on for the last 4 years, 5 years is quantum repeater networks. And in particular, my interest, my background being as a systems person rather than a quantum physicist, is in how we're actually going to scale these things up. So between the theorists at the top and the experimentalists at the bottom, there's this really huge gap, and the stuff that's in the middle is architecture and engineering, and that's the stuff that the physicists tended to sort of write as a lemma in their papers. Somebody will take care of this, right? Well, I'm the guy who wants to take care of this. Okay? So we've got a bunch of interesting stuff, I think, results from various things. The general concept I want to talk about, the overall architecture I want to talk about today, is a thing we call recursive quantum repeater networks. I'll give you sort of the preview of it. If you've got a large network of where each of these nodes is a quantum repeater, and between them you've got a set of links, right? It's actually a collection of networks. It's a network of networks. That's what we mean when we say internetwork, in fact, right? So you'll have different sorts of concepts. You'll have transit networks. You'll have some network where your request originates. You'll have some network where it actually terminates. And in particular, since what we're talking about is recursion in networks, each of these individual nodes here can in fact represent a network itself. So inside of that, at the higher level, when you are planning your requests and controlling your overall interaction throughout the system, you can treat an entire network as a single node in the system, and that's where you get your scalability. So this was work that Claire and a friend of mine named Joe Touch, who's at USC ISI, the three of us did together about 1.5 years ago and appeared last year. If I'm boring you, you can just download the paper and take a look at that while we're talking instead of listening to me. Let's see. And Joe's background is actually, he's a classical networking guy as well, and he's actually the guy who came up with classical recursive networks, some of which I'll talk about a little bit later. So overall, my group, we call the group AQUA, which stands for Advancing Quantum Architecture. And we work more or less in 5 areas. The overall paradigm of what we're working on is distributed quantum computation, because I believe that individual systems, are not going to scale to the levels that we really want in order to actually solve what you would call, I suppose, commercially relevant problems. Right? So we're interested in the design of these large-scale distributed systems. That includes things like, we've actually done some design of individual devices, which I talked a little bit about informally the other day. Some of these are like nanophotonic devices and things like that. A lot of this work is done in collaboration with guys at Stanford. Done work on workloads, and by this I mean taking applications and figuring out how well they will run on a given architecture, as opposed to actually defining or creating new quantum algorithms themselves. Principles, meaning things like understanding how the principle of locality from classical systems actually applies to quantum systems. Designing things like the quantum multicomputer. Designing layered architectures. So applying what we classical architects think of as standard engineering practice, figuring out how that's going to affect the overall architecture of quantum systems. And finally, some software tools, and you'll see a little bit about some of those over the course of the day today. So, by the way, let's see. So we're scheduled on the schedule's written till noon. What time do you actually want me to stop?
I'm not sure how long I've been doing this. I'll check while you talk.
Should have asked this before we started, but
Maybe look, I have to go out a little.
all right. So let's see, networks. All right, so what are quantum networks actually useful for? And by the way, feel free to make this interactive. Feel free to interrupt me and ask questions. I actually like to make a talk interactive. So what are quantum networks and what do we need them for? Well, so the first sort of thing that obviously comes to mind is we're going to do distributed numerical computation. And here you're talking basically about more computational power and the sheer scale that comes from actually combining systems. And this was more or less the original ARPANET vision of distributed shared computing resources. In this sense, we're talking about quantum multicomputers, maybe distributed quantum databases, things like that. And at this level, we're probably talking primarily about quantum system area networks and local area networks rather than wide area networks. Although the real focus of today's talk is really about the larger scale networks. For wide area networks, for example, one of the things that might actually be done, a form of what you would call numerical computation, is excuse me, a form of quantum Byzantine agreement, which has been developed in theory, and in fact was actually demonstrated experimentally a few years ago as well. And the goal of something like that is to accomplish a task in fewer rounds of communication in the quantum sense than can be done classically. Okay. Overall, we expect that there will be a lot more numerical uses for Bell pairs, GHZ states, W states. And we would like to see more development of these sorts of things in the overall literature for these uses, distributed uses of things. One thing that's been talked about, you guys probably saw it, showed up in Science a few weeks ago, was blind quantum computation. This is a good experiment. The theory was developed several years ago. Experimentally, it was demonstrated recently. Using an optical system. They divided the system into a quantum server and a quantum client. And in the system sense where this would fit in would be essentially a computing platform from our point of view. It's not a specific algorithm, but it does fit into the overall structure of networks as we're talking about it. Okay. Let's see. And this, by the way, this assumes measurement-based quantum computing as a model. That's built fairly deeply into the concept of blind quantum computation. Survey says?
Unmeasured quantity.
What's that?
It's an unmeasured quantity. The one next to us is free. Ours won't talk to us. Let's assume we're okay.
Okay. Let's see. So the flip side of the coin, those first couple of things I talked about was distributed numerical quantum computation. The other side of the equation is actually using quantum effects when you can build distributed quantum states for executing tasks that you wouldn't necessarily consider to be computational tasks, but that come building, in effect, things like sensor networks, quantum sensor networks or the like would qualify in this area. Quantum key distribution would certainly qualify in this sense because effectively what you're doing is you're actually measuring the presence or absence of an eavesdropper in that sense. And Shota Nagayama, who's sitting in the back, his bachelor's thesis was actually figuring out how to take the keys generated by quantum key devices and integrate those into the use of IPsec for actually keying an IPsec tunnel. So following on from the kind of work that was done by the BBN guys, including Chip Elliott, and they sort of hacked the protocol. We decided we wanted a slightly more engineered protocol, and we've written an internet draft for this. We haven't gotten it to RFC status yet. But that would be one example. Another one that came out last year, which I was really thrilled with, was Daniel Gottesman showed how you can take distributed Bell pairs and use those to improve the precision of measurement of optical telescopes. So doing effectively interferometry where your reference standard is Bell pairs rather than some sort of distributed classical signal in that sense. Truthfully, this is a fabulous thing. I think it's a really wonderful thought experiment. And I actually talked to Daniel about it. And in order to pull this off, you're probably going to need a minimum of 10 to the 9th bell pairs per second, maybe 10 to the 10 or 10 to the 11 bell pairs per second. And the networks we're talking about here, right, the experimentalists are going, in 5 years we might get to 1 hertz, right? So we're still a couple of orders of magnitude away from actually pulling this off yet. But as sort of a goal, it's a good place to go, I think. And one idea that I had a number of years ago, but we haven't actually pursued yet, actually in the eastern part of this state, whichever way east is, there's the LIGO, the Gravity Wave Observatory. Could those guys use it? If we created a network that generated entanglement between Washington and Louisiana, where the other observatory is, could they use that to improve either the resolution or the sensitivity of their detector? Talked to Gerard Milburn about this a little bit, and he's like, yeah, that seems feasible. It seems like something we could do, but nobody's actually sat down and done the work yet. The reason this came up was because, in fact, those guys use already, they already have implemented and in production non-classical states of light in their detectors. They use a form of state called a squeezed quantum state. And I don't know that anybody has yet figured out how to go between entanglement and squeezed states, but the guy who would probably know would be Akira Furusawa at the University of Tokyo. Anyway, speculative use. Okay. So, preview of what I'm going to talk about, or sort of the results here. I want to emphasize that quantum networking is distributed quantum computation. And we think of a network, we really think of transmitting data from one place to another and as sort of a passive activity. But in fact, for quantum networking, this is not just forwarding of data. The creation process of creating these distributed states is in fact a distributed quantum computation itself. And I really want to emphasize that. The classical principles for how we design classical networks, my sort of way of working, my approach to solving problems is to figure out what known classical engineering principles we can apply to the quantum systems, figuring out how things change in that sense. And we've been actually pleased to see that largely the classical networking principles apply. And we'll go through that in some of the detail in a minute. That includes things like layering and multiplexing, resource management, finite state machine-based design of the protocols, all the usual approaches to things. Now this one comes from our collaborator, Joe Touch. Joe believes very, very strongly that recursion is a fundamental property of networks. It's not something that's sort of tacked on. It's fundamental to the behavior of the networks themselves. This is particularly valuable for internetworking between networks. It's part of how you actually get to scale in large-scale systems. When I saw Joe's work on this, I realized that it applied very well to what we want to do in designing quantum networks, and so we've adopted the concept pretty much wholesale. So, outline what we're going to talk about today. I'm not sure if I really need to go through the first part, talking about networking and what's so hard of it. Parts of this talk were engineered for quantum folks. Let's see. We've got one hardcore quantum guy here. I don't know about you. Everybody else here has strong background in systems, right? So we're actually probably pretty much okay in that sense. Talk very briefly about 4 types of quantum repeaters, quantum repeater network architectures, and then go in particular into the results that I really want to show, which are about routing and multiplexing in networks, and then the discussion of the recursive actual quantum network architecture. Okay. So, networking, what's so hard about it? We can sort of skim through this part of the stuff, I think. Naming, resource management, heterogeneity in both technology and resources and operations. This is one that would never even occur to the physicists. Like, well, Microsoft owns one network, Google owns another network, Layer 3 owns another network, Cable and Wireless owns another network, and they don't really want to talk to each other more. They don't want to tell each other more than they have to, in particular about the internals of their network. Right? So we need a system that's actually going to accommodate those sorts of things. Dealing with out-of-date information is, of course, a big deal in networks, and sheer scale. Okay, so naming. What is it that actually has to be named in a network? Well, nodes, networks, processes, users. Memory location, the request itself is a particular issue in quantum networks that differs from classical networks, and you'll see why in a few minutes. And things like the scope of the name also matter. The semantics of a name can vary in types of networks, and that means that you're going to have some sort of resolution mechanism as well that translates from one namespace to another namespace. Something like ARP or DNS would be two examples of a namespace. Resource management, avoiding overcommitment of your resources, something we all want to achieve in classical networks. It's going to be different in quantum networks in some ways, but we want to do that while making sure that the overall network is in fact efficient. We need to balance the fairness while minimizing the average weight and maximizing the throughput of the system, right, for competing requests in a network. Enforcing real-time communication is actually difficult without some sort of hard reservation mechanism, meaning circuit switch, int serve as opposed to diff serve, something like that. And in quantum networks, because the quantum information itself is so fragile, in fact, that real-time component actually figures pretty strongly into the overall system. Heterogeneity, physical technology, of course, bandwidth, pulse rate, quality of the channel, everything else all varies. This can be also, whether it's single pulses or strong laser pulses that you're actually using as your physical mechanism for actually doing your entanglement protocol there as well. Heterogeneity in your architecture, whether it's dealing with packets or circuit switching, what have you. Resource and network conditions, your length, your buffer memory, all that sort of stuff varies. Management and operations, and autonomy, which goes back to what I said about Google, Microsoft, cable and wireless, everybody, right? They want to have autonomous operational control over their entire network. Dealing with out-of-date information, dynamic state connection, dynamic network state, the topology of the network itself, which links are up and which ones are down, right? You don't want to track the entire thing. That sort of stuff. Sheer scale, billions of nodes, millions of networks. Individual nodes can't and shouldn't track the entire state of the entire network. It's just not feasible for something that's on the scale of the internet. The way we generally solve this in classical networks is by applying a form of hierarchy. The thing that's sort of most obvious in that sense is the difference between the internal gateway protocol and the external gateway protocol at the level of the global BGP, right? The border gateway protocol for this internally, or across the entire internet. The challenge in doing this is maintaining efficiency and robustness in the overall system. And Joe would argue that the right approach to doing this is actually applying recursion at the system as a whole. Because in fact, what we have seen, the ARPANET was originally one network, and then it went to 2 layers, and then you could argue that it's effectively 3 layers now. You've got the global BGP layer of interconnections of autonomous systems. Beneath that, you have individual organizational wide area networks, and then underneath that, you've got a set of local area networks. If we apply the same set of engineering principles at each of these layers, we can build a strong recursive architecture which shares a lot of knowledge and engineering efforts so that we don't have to re-implement things separately at each layer. Okay. That's everything about classical networking, but you guys all knew that. The 4 types of quantum repeater architectures. I'm not going to go into the details of each of these types. You can get these from the papers, of course. Purify and swap architecture was originated by Wolfgang Durr and Hans Briegel and others going back to about 1998. Various people have done lots of contributions to this. The group that I have worked with, Thaddeus Ladd, Bill Monroe, Kaya Nemoto, have done their share of work on this. Others include, let's see, the group of Misha Lukin at Harvard would be very strong, both experimentally and theoretically, on a lot of this work. There are some parts of their work that I really think are excellent, and other parts where I'm not sure that their conclusions are justified by the data that's presented in some cases. So good things and bad things about it. CSS encoded systems where you're literally, instead of doing purification, which is a very simple form of error correction, doing full-scale quantum error correcting codes, on top of the physical entanglement mechanism. Liang Zhang, who at the time was a student of Misha Lukin's at Harvard and is now postdocing at Caltech, has done some good work on that. Bill and Kai and I are co-authors on that particular paper of Liang's. Let's see. Surface code quantum computation. So Austin Fowler, whom we all know as the primary apostle of surface code, the man who's figuring out how to make it all work, realized at some point that this could actually be applied to communication systems as well. And it could be applied to repeater architecture as well as to actual computational architecture. And again, Bill and Kai and I are co-authors on this as Austin developed this out into a repeater architecture. These architectures have interesting differences in how synchronous communication is required across the entire network architecture, which has a big impact on your overall behavior of your system. And the last one would be the quasi-async system of Bill Monroe, which he published in Nature Photonics a couple of years ago. And I can't claim, I wasn't involved in that one, but there are some very good, very interesting ideas in that one overall. So, let's see.
What does the word quasi mean here?
That's my term for this. You can go. Bill claims the entire architecture is fully asynchronous, and I don't think I really 100% believe that assertion. That's pretty much all the quasi means. You'll see in the behavior of a lot of the repeater networks, there are a lot of cases where, for example, when you're transmitting a quantum pulse, you send it across the fiber, and then you have to wait until you get a response back to whether or not that pulse actually arrived at the far end before you can do something with it. So that would be synchronous behavior. Bill claims that with this new architecture, he can do an awful lot of stuff where he sends the pulses, and then each node can operate entirely asynchronously and entirely autonomously with the behavior of it. There are a couple of places in it where it remains more or less, rather than truly asynchronous, self-clocked might actually be a better term for it, because the extra nodes in the system essentially receive information from their neighbors, but they don't get to operate totally autonomously and totally asynchronously. There are places where still round-trip latencies wind up showing up, but it's round-trip latencies over a single link rather than end-to-end. And so the individual nodes then get to behave more differently in that sense. So that's a very crude explanation of it, and Bill would certainly take umbrage to anything I said about it. But
in absence of global synchronization.
Pardon? Say that again?
It's kind of local synchronization, but not global synchronization.
Right, in that sense. It's link level, so single hop level sorts of stuff. So, most of what I'm actually talking about, most of the work we've actually done in terms of simulation is actually on the purify and swap form of quantum repeaters. So that's actually mostly what I'm going to talk about today. And what they need is a little bit of quantum communication, quantum memory, local quantum gates. Well, pretty much this is true for pretty much all repeater architectures. Lots of decision making, both local and distributed, and lots of classical communication. We'll see how this sort of all comes out. Oh, so I should probably say, the differences between these, one of the key differences, the original purify and swap architectures were developed assuming very small numbers of qubits in each repeater node. Like the Harvard gang has defined an approach for this that works with 2 qubits in a repeater node. And they want to do this literally with 2 physical qubits. You can't run error correction on 2 physical qubits. So the purify and swap stuff at that level looks much less resource intensive, by orders of magnitude. The problem, of course, is that because it requires synchronous communication, now you have to have long lifetime memories. And that gets to be a very difficult problem. So if you then want to turn around, what you would really like to do is take each of those qubits after it arrives at the repeater node, upcode that into a large encoded state so you can keep it for the tens or hundreds of milliseconds it's going to take for your round-trip messaging, and then code it back down. doing all of that analysis and figuring out all of the resources involved in this and the execution time for everything and the error probabilities for everything, overall is a big engineering problem. And although we have ideas, nobody's really done an analysis that's really complete at that level across all of it for really any of these architectures at the level we would like to see it ultimately. But it means that, so this one looks like it takes tens of qubits per, this looks like it takes a handful of qubits per repeater. This one looks like it takes tens. This one looks like it takes hundreds. Bills, it's not entirely clear, but it should be a small number. But by the time you apply enough error correction, enough of everything else that's going on, the resource analysis, I think we've done the first level analysis, but we really need to go the next level and make it much more detailed as a community. Let's see. Let me show you just to sort of set the idea here. This is one network link technology, again developed by Bill Monroe and Kai Nemoto and Tim Spiller. Bill and Tim were at HP Labs in Bristol at the time. Kai is in Japan. The QBus technology for this, and what you do with this one is rather than sending single photons, you use actually a moderately strong laser pulse, which you put into a waveguide of some sort, which is coupled to a qubit at one end and at the other. So the distance here might be millimeters. It's effectively what we were using in the distributed architecture I talked about the other day. It might be kilometers. But the loss in this channel is still limited to a few dB, which is a problem in terms of implementation. What this does is it effectively measures the parity of these two qubits. And what you get out as a result when you measure it is, in effect, the parity of the two qubits, but with a lot of noise, and so you get relatively low fidelity out of this when you come out. So simulations of this are in Thaddeus's paper in New Journal of Physics, and the original idea was in Bill and company's paper in the New Journal of Physics, and this is also what we have used in a lot of our own simulations following on from it. So, just showing you again, what you get out of this is effectively this entangled state here at the end. Okay. Now, entanglement swapping. Have you guys seen entanglement swapping before? So entanglement swapping is using teleportation to lengthen the distance of your entanglement. So we got 3 stations in the diagram here. Each of these arrows represents a qubit. Right? So you run your single hop protocol to create bell pairs between station 0 and 1 and between station 1 and 2. And then you run what's called entanglement swapping using what's called bell state measurement between the two of these. You measure which of the bell states you think that pair of qubits is in. The result of that is you lose your local entanglement and you're left with long distance entanglement. Problem, the results of this bell state measurement actually have to be communicated into the opposite ends. So this is why you don't violate relativity when you're actually doing this. Okay. Bigger problem, fidelity decreases when you do this. And so that means that after you've done it, so you start with reasonable fidelity entanglement. After you do this, you're going to have lower fidelity. That might be okay over 2 hops. It's going to be a problem if you're talking about 1,000 hops. This is the nested purify and swap architecture that was designed originally by Dürer and Briegel. If you go back and you read those original papers, as a systems architect, it becomes a little bit hard to tease apart where the entanglement swapping is and where the purification layer is in the overall system. They've got it essentially as one integrated sort of system. The protocols are sort of bound together. But what you do in this nested approach, if you've got 4 hops, you do entanglement swapping between at station 1, which connects to 0 and 2, and at station 3, which connects 2 and 4, and then you repeat. You wind up freeing those qubits in the middle, and you end up with the longer end-to-end distance. Much of the original analysis was done assuming a power of 2 number of hops. This approach obviously works better when you've got 4, 8, 16, 10, 24 hops. So, purification. We'll start with 2 entangled pairs, So this is one entangled pair held between station 0 and 2, and another one held between 0 and 2. Perform some local operations at each end between these two. A local operation basically amounts to a C naught followed by a measurement. You measure out 2 of these qubits here, you get some classical results. If it all works, what you're left with, the pair you're left with, has higher fidelity. But again, your results have to be communicated, and the usual protocol means you need actually two-way communication, or 2 one-way messages, actually. Okay, so that's sort of the basic idea. Those are the real concepts you need to understand this. I looked at this and said, well, what you need is you really need a protocol stack. You really need to understand how this overall thing fits together. So we designed this. Physical entanglement layer at the bottom. Above that, your direct message is saying whether or not your entanglement operations actually worked. Entanglement control. Then above that, purification control and entanglement swapping control. So interestingly, these wind up being applied recursively over 1 hop, 2 hops, 4 hops, 8 hops, which is why we think one of the key reasons why we think the recursive network architecture actually works well for this. And then at the top, you'll have some sort of application protocol, which might be your quantum key distribution or whatever it is. Okay. Now, interestingly, so this is done at the distance 1. Both of these are only over a single physical hop. These parts, this part is repeated at different distances, and then again, you'll need some stuff end to end. Out of this entire stack, the only part that's quantum is this layer here at the bottom. Everything else is classical messages, which means that everything else is messaging and distributed computation, the kinds of things that the people in this room are experts in, rather than the experimental physicists who are trying to actually implement some of this stuff. So that's sort of where the division of work would be in terms of a community. Okay. Let's see, 4-hop stuff. I think you see probably how this interacts. You'll wind up with purification control and entanglement swapping control happening over 1 hop and over 2 hops, as well as end-to-end over the course of this. That's all at the relatively abstract level. So let's look at this where you've got multiple qubits involved in the system, and you'll start to see how the complexity of the system actually grows as you're doing this. You're sending a bunch of pulses. You'll wind up with some of your qubits entangled and some of them not as you're doing this between the various stations. And then what you're going to do, you have to pick out pairs of these and run your purification protocol. One of the places where you have to be careful in designing the overall system is this guy and this guy have to make the same decision about what pairs they're going to purify. If he picks 1 and 2 up here, and he instead picks up 1 and 5, then your purification operation is not going to work, and you're going to have a real problem in your overall distributed system. Okay. So now there are different ways you can achieve that. You need to analyze the set of information that's available at each station and make sure that either they can independently make the same decision, or if not, that they are going to communicate and share enough information to make that decision. Okay. After you do the purification, of course, you're left with fewer of the actual entangled pairs. Now, same sort of thing going on up there. We get a few entangled pairs. In this case, the color, we went from yellow, which is sort of an intermediate fidelity pair, to green being a higher fidelity bell pair. And now here in the middle, green is good enough, we said, for doing entanglement swapping. We'll do the entanglement swapping there, and you get the longer distance stuff there. Again, you have to have enough information to make the correct decisions everywhere. Right? This station 2 in the middle knows enough about these bell pairs to make a good decision here, but 1 and 3 don't know anything about what's going on at 2 until 2 tells them. Right? They don't know what decisions 2 has made. And in particular, 1 probably doesn't know anything about the connection between 2 and 3. Right? That's an important sort of information hiding principle involved there. And that's pretty much it on the basic operation. So that's sort of all background. That's, with the exception of the protocol stack itself, that's all work that everybody else has done. let's see. So let me show you some of our actual results. Some of this was the bachelor's thesis of one of my students, Takehiko Sato, who's now finishing his master's degree at the University of Tokyo, and Lucio Aparicio, who was doing his master's degree at Todai but was working with me. Routing. You guys know this. We want to create entanglement between A and B in this network. How do you decide how to get from A to B? What would you use to decide on how you're going to get from A to B? Yeah, sure, path selection algorithm. How about Dijkstra's shortest path first? Okay. The problem is, in a quantum network, we don't know what the cost metric is. We don't know how to actually figure out what that best path is. Okay. Let's see, 4-hop network here. Circle is pretty good, X is a pretty poor network, and triangle is sort of an intermediate length. Right? The cost for this path would be some function of those link costs, right? Now, what is that? In classical Dijkstra, the cost would just be the sum of those individual links. With quantum version, we don't actually know sort of a priori what the right way is to combine these in order to get some reasonable cost for the overall path. Okay? So let's look at the link cost. These are a set of simulations. This was of Q-bus interconnections over, I think these were over 10 kilometers, but with some additional loss thrown in. So the x-axis here is dB loss in your channel from one end to the other. And the vertical axis here is then throughput of bell pairs purified to a particular fidelity. So in this case, all of these bell pairs have been purified to a fidelity of 0.98. And once that's done, then they're delivered and they're counted as part of our throughput here. So you can see as loss increases, the blue line here, your throughput is going to decline. And in fact, it seems to decline in a stair-step fashion. This is a result of the number of rounds of purification you wind up doing. So this would be 1 round of purification, 2 rounds of purification, 3 rounds of purification, 4, give or take, roughly. So the blue curve here is the throughput, and this is a couple of hundred bell pairs per second. The green curve here is the number of measurement operations done in the network as a whole. So this is single hop stuff, so this is at the 2 ends of our single hop. The red line is the number of pulses you put into the fiber. So in classical networks, particularly if it's like an Ethernet or if it's like an OSPF network or something, throughput is usually used as your inverse metric. So 1 over throughput is the cost for actually using a link in OSPF. The protocol is independent of that, but that's the most common definition that's used, and that was defined by Fred Baker, who's past chair of the IETF. Okay? So that sounds good, right? 1 gigabit per second, that's 1 bit every nanosecond, sounds good. We can't use a direct approach like that in the quantum networks because we don't know a priori what the fidelity of the link is going to be, whether it arrives or not, once it gets there, whether or not it's useful. So in fact, we have to sort of move up a level and find yeah, sure, question.
So I have a stupid question.
No stupid questions. There are no stupid questions in my world.
So in traditional communication, if I need to communicate a message to you now, I need some bandwidth now. Right. Whereas, isn't it true that in quantum, I can say, okay, I will need sometime today, I will need to communicate a message. I can actually buy the bandwidth, pay for the bandwidth now, and communicate it later without paying at the time of really communicating. Right. So that means that some of the measurement that we do, especially for throughput, are kind of different. Because when we're talking about traditional, I know that I'm running my application now. If I don't get this amount of traffic within a second, someone is going to be waiting. Right. Whereas it's not so much true in this case, right?
You're absolutely correct. And in fact, one of the things that comes up, particularly as you talk about scaling up the networks, is figuring out how to map operations on the network to a particular request, because what you're doing in this kind of quantum network is you're creating very generic end-to-end states, right? And so I want to create one between I'm going to need 100 bell pairs between Seattle and LA, right? But the link between Portland and San Francisco, all it's doing is creating bell pairs, and it doesn't know whether those are to be assigned to my connection between Seattle and LA or your connection between Vancouver and San Luis Obispo.
It's a completely different marketplace, because
It
to the
is.
extent that the hubs in the middle, they will be creating entanglement all the time.
Yeah.
And
Over a single link, that's really easy. It's really obvious that the sinks ought to just run flat, that the individual links ought to run flat out. They ought to be trying to create entanglement all the time. The question comes in for things like the entanglement swapping. It's like, well, now do I connect point A to point C, or do I connect point A to point D? Which one's the better thing for me to be doing right now? So yeah, absolutely, you're 100% correct, and that's the kind of problem I want to solve. And if you want to work on it, great, we'll work together.
But there's an additional factor in the quantum case that you can't have these things hanging around waiting. Because as soon as you stick quantum states in every video. So
what is the time frame for that?
It depends.
it depends on what type of memory you've got. So if it's a raw qubit gridlock in nanoseconds, error correction is costly, and quantum memory is incredibly costly. So you wouldn't want to pay now and get 10 bell pairs and use them in an hour, because keeping them at a high fidelity for an hour will cost you an awful lot.
Yeah, so the service providers will probably charge you to store those qubits in the meantime, right?
Is it something that, due to the technology that we have now, or is it true to believe that this is the reality?
This is reality, because this is why, so the reason why quantum mechanics and quantum computers are difficult to build is that quantum systems will interact with anything that possibly can at any possible opportunity. And quantum memory is stopping them doing what they want, and that is always going to be difficult.
But yeah, it's so. We used to batch email via UUCP and Usenet and everything else in the middle of the night, because that was when the networks weren't being used, right? In this marketplace, so maybe I'll ask for 100 pairs to be ready by 6 a.m. or something, right? But then if you don't use them until noon, you got to pay somebody to store them until noon, right? That's definitely the kind of thing we want to evaluate. Right, so this still is this is over a single link, right? What we're looking for here is a metric for our link cost. So it looks like in this case, both for a single hop over this, the number of pulses and the number of measurements both look to be sort of reasonable metrics compared to this. They sort of go up as throughput goes down. We'll see though that one of these actually winds up being a slightly better metric. For the purposes of these simulations, we picked out 4 points on this curve that were just chosen arbitrarily. We said, in our network, there are 4 types of links. There are 4 links of 4 different qualities. That's where they are. Okay. First set of results. The gray bars are throughput. Well, let's see. So the x-axis here, this is a set of paths that we actually simulated, and what you're looking at here. For example, square, triangle, 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 which is here somewhere. That would be a path with 1 excellent link and 3 good links in it. Right? So this is the set of things we did. And then across this, they are ordered according to throughput. Throughput is the total distance here, or the total height there. And then the 2 measures of work that we used, the number of pulses in the channels and the number of measurement operations. This is across the entire path in that sense. And again, sort of qualitatively, you can see that there's a pretty good inverse correlation between the two. A little more detail. These are for 40 different paths, the same 40 paths that are in this diagram here. But these cover distances ranging from 1 to 9 hops with different combinations of total different combinations of high and low quality paths in this. And the x-axis in this case is path cost calculated using the path cost using number of measurements here as your link cost for each of those individual costs, and then just summing those to get our path cost here. So this is inverted, so low cost paths here, high cost paths there, and you can see that as the cost increases, that throughput declines. Okay. The different colors of marker here, these with the red X's are all paths that contained one poor link in the overall system. The green ones were paths of different lengths that were all the best quality paths, and you can see this sort of relationship here. They tend to group according to the bottleneck link, which in terms of throughput is the way a classical network actually behaves. So in terms of throughput, we're seeing something that looks a great deal like what we would expect in classical systems. That's reassuring. On this side over here, comparing the total cost, again, the same set of things. Number of measurements here on this line and total number of pulses in the green triangles. And you can see just from looking at this that in fact the measurements are actually going to be a more consistent overall measure of your total cost. They tend to hew more closely to an actual line than the green ones do. And statistics on that are in the paper. So we've got strong correlation between the path work there. Those were for different lengths of paths from 1 to 9 hops. This is all of the possible 4-hop paths, all 256 of them using our 4 data types. And again, you can see here really clearly, you can see that the throughput's definitely determined by the bottleneck link. And you got really, here it's even more clear that the measurement number as opposed to the number of pulses is the right metric for link cost. This in particular takes into account the fact that measurements are used for Bell state measurement and for the actual entanglement swapping as well as for the purification, which the number of pulses can't really take into account. All right, so results of this chunk of work. This was the first work to really quantitatively evaluate the behavior of heterogeneous paths. Pretty much everybody else sort of said, yeah, sooner or later we'll have to do that, but they all assumed homogeneous stuff in their networks. And as far as I'm aware, we're the first to actually consider path selection in topologically complex networks and how you would choose an appropriate path for something there. Counting the number of measurement operations winds up being a good metric for the total cost to the network, to everybody in the network as a whole to create this. And so that winds up being something that's well worth evaluating. And the throughput of that individual link makes a good cost metric for the link. And the additive path cost actually turns out to work pretty well. So summary of that, quantum Dijkstra seems to work pretty well. And I'm sorry Burton isn't here because he actually said quantum Dijkstra the other day when we were talking about that. Too bad. All right. Next chunk of work, I'll show you this one. We may not actually really get into the recursive stuff unless you guys want to stay until 12:30 or something. Let's do the resource management real quick. Remember, this is some sort of distributed computation, and this fragile memory means we've got a real problem here. Right? So does this require some sort of circuit switching? This is another sort of resource evaluation system, resource evaluation of the kinds of work that I like to do in this. Multiplexing scheme, you guys know this. Let's say we've got a dumbbell network here. We want one flow to go from A to B and another flow to go from C to D. Right? We can do this using circuit switching, which means everybody else is going to have to wait. We can do it using time division multiplexing, where you just sort of flip back and forth between the two for a while. Or we can do buffer space multiplexing and take half of the memory at the intermediate nodes and say, well, we'll dedicate this to this one. And again, it's going to require some sort of reservation mechanism to actually do this. This is, in fact, the network that we simulated for this. And what you see from this is we actually investigated mechanisms where we dynamically adjusted the target fidelity for each of these individual links. So most of these simulations so far, we said we'll only use a bell pair after we've purified it to a fidelity of 0.98, which means over every distance we applied the same kind of thing. In this case, we varied this on the middle because the middle is the bottleneck link, right? Well, so maybe we should find a way to sort of minimize the use of that at the expense of making AE, CE, BF, and DF work harder, because in something like the circuit switch scenario or even the time division multiplexing, those links are going to wind up being idle a bigger fraction of the time. And we might as well take advantage of what they've got. Right? So, and in fact, what we did find in the process of doing this was that if you multiplex this correctly, you'll wind up with substantially better overall system throughput for multiple connections. Let's see. Larger networks. Even the dumbbell network is, to the best of my knowledge, the most complex, topologically complex repeater network anybody has bothered to simulate, even at that simple level. This one, more complex network. What we want to do is, we've got a half a dozen flows that are running through this, 1, 2, 3, 4, 5, I guess, running different places. The blue set of lines is one flow. The oranges is another. And part of what we're looking at here is, in this case, we've got some short flows and some longer flows. And one of the things we want to know in the process of doing this is, can the network be fair? Will short connections wind up driving the long connections out of business, depending on how you actually do the multiplexing scheme? Right. Let's see. What we found while doing this is this would be peak ideal throughput. So in this case, so each of these colors represents the throughput of the matching diagram. On this case, this is the entire network is dedicated to just the blue. This is the entire network is dedicated to just the red connection, which is also a long distance connection here. And the shorter ones, obviously, you see more. So this would be, if everybody could get the maximum bandwidth they managed to achieve, our network as a whole would achieve this. Right. That would be some sort of ideal case. When we take just the two pairs, each of these two pairs actually gets greater than 90% of its own ideal throughput. So the degradation to one connection as a result of the introduction of a second is less than 10% in this case. And a couple of other cases here. As the total number of flows you add in increases, of course, each one gets penalized sort of more. One of the things you can see, though, is that even for some of the longer distance ones, in this case, you can see here, the longer distance one succeeded in retaining 77% of its throughput, whereas some of the shorter ones actually suffered a little bit more of a hit in their throughput, which is actually sort of a little bit of a surprise, counterintuitive. So let's see. So how can we evaluate this? Let's see. So this was for time division multiplexing here on those. Same sort of thing for statistical multiplexing. And in fact, in this case, we actually got better overall throughput in the statistical multiplexing case, which is essentially the behavior of the internet as opposed to cell phone network. So statistical multiplexing in this case we actually think works better. And buffer space multiplexing, this is the case where the intermediate nodes sort of split their memory out, turned out to not work quite as well. We actually did evaluate the fairness of these using Jane's fairness metric to see how the different flows actually competed. And we actually found that, somewhat to our surprise, that actually all three mechanisms retained very good fairness in that sense. So we're actually pretty happy in that sense. And we think actually that the statistical multiplexing gives the overall best system throughput. But the biggest question is that memory lifetime issue. That's one of the things that needs continued analysis.
X1, XN, those are tracking.
Pardon?
The X1 through XN.
Those are, in this equation, throughput in bell pairs per second. All right. This part I'm just going to flash through, but I wanted you all to see sort of part of how we did this. You won't see a finite state machine with state transitions and triggered sorts of stuff in the work by the physicists, but it's the way I like to design protocols. Right? So different layers of this stuff. All right. So that's sort of everything about quantum Dijkstra and about multiplexing. Any questions on those two topics? Let's do about 10 minutes on the recursive stuff, and then we'll call it and then. How about that? Does that sound reasonable? Let's see. Okay. Thanks. You can get the recursive stuff by looking at the paper.
Or the video.
Or the video, yes. So Joe, like I said, insists that that recursion is a fundamental network property. It's not just some sort of engineering artifact for the way we build things. It unifies the overall architecture of the system and provides new ways to go about doing tunneling and overlay networks and multi-layered networks of all sorts of things. Let's see. I'm just going to flip through this. We'll skip some of this stuff and go straight to the quantum parts. So the quantum stuff. Here's our recursive network, the diagram that I showed you at the beginning. Again, we've got transit networks, recursive networks, individual sorts of things involved here. Let's say in this case what we're trying to do is we're trying to create an entangled pair between a couple of these nodes. Or actually, each of these pink nodes would be in what we're trying to create as a one large entangled state between those n nodes of the system. Okay. Let's see. And for a simpler example, we'll look at just these half a dozen nodes here. We're going to start with a request that originates here. And what we're asking for is entanglement between node 11, node 55, and node 77 in this overall architecture here. Now, the way you would do this is, so we're looking for a state that would result from a circuit like this, where the circles are controlled phase, controlled Z gate. We want to create this over a distributed system, right? Now the question is, how are you going to go about doing it? One way to do it would be to create this 3-qubit state, all of it here at the node 11. This is the guy who's essentially controlling your distributed application. You can create them all here, and then teleport 2 of the qubits from where you are to the far ends of the network over top of bell pairs. Is that the most efficient way to actually do the overall system? Well, it might actually be better if we started with it in the middle and then spread it out, right? Which of these is more efficient? In order to understand all of this, you have to have routing tables available to each of these guys. They have to have some amount of understanding of the overall system. Right? So here at node 11, it holds a routing table that looks something like this. It knows how to get to network 5 and how to get to network 7 out of this via other networks in the system, sort of a relatively standard routing table sort of approach. The guy in the middle here is going to have a somewhat different routing table, of course. Neither one of them would understand every node in the entire network. Right? So what we're going to do is we're actually going to rewrite this request. So we'll start with this. Here's our request. So we want to have node 11, node 55, and node 77 all in this entangled state. And the guy who creates this request is going to say, when I'm communicating with you about this request, we'll use the address 1000 to refer to the qubit. This is effectively the memory address, virtual memory address for the qubit that's involved in this state. Okay. So we're going to take this and we're actually going to rewrite it into the set of operations for doing this. Overall original request, well, we can divide it up into 3 teleportation operations, and each of those teleportation operations can then get split out into first the creation of a set of bell pairs, and then the actual combination operation here at the end itself. So we're going to have this overall set of states here. Okay. So doing this, why is this valuable? This provides ideal support for internetworking, we think, and this will allow or support hierarchical routing of operations very smoothly, and it will unify these software implementations across multiple levels. So in this case, the request that you've got, so this guy knows here in the middle, when he's doing this, I want to teleport from 1 qubit, network 5, address 2000, network 5, 3000. We want to get that to node 55, 1000, as it's drawn here in the original network diagram. Right? So that's node 55 out here. The original request from node 11 knows the address and name of these individual nodes, but it doesn't know the names of other individual nodes throughout the entire network. So it starts with a generic request that says, somebody here in the middle, connect me to that. And that rewrite rule, those rewrites can happen in various places throughout the network. Okay. So let's see. What's interesting about this, it essentially unifies the distributed computation with transmission of data. So the teleportation operations, we need to be able to request in order to make even just bell pair creation work properly, we have to be able to request purification, which includes C-naught operations and dependent operations or conditional operations dependent on the outcomes of things like measurement operations. So we've already got C-naught, measurement, and conditional operation. Extending from there to a fully general distributed computing mechanism is actually a very small leap from there. So what we really want to do is we want to just go ahead and do the extension of that and create a unified distributed mechanism, which means that this guy at the end can request of nodes in the middle of the network or of networks in the middle of the network, please create this state for me. And here's a recipe for actually doing it. Too bad Alex left already, because here's this diagram is actually from Bill's paper on some of the asynchronous stuff. And this gap here, this timing gap here, depends in part on the single hop latency in the network. And that's where some of the quasi-asynchronous behavior comes through it. This diagram's from Bill's paper. And what they said was, one way to create good end-to-end bell pairs is to start from the middle of the network and then propagate them out via teleportation until you've got end-to-end. Okay? It's great in theory. The question is, in a billion-node network, how do you find the middle? What's the middle of the internet? Right? What's the middle of a connection between here and Tokyo? We need approaches to doing that. Right? So here's your network as a whole. Where's the middle? All of this can be done ultimately with one single software module. One of Joe's papers on recursive networks actually includes the pseudocode for doing essentially all of networking as one recursive function for doing this. And basically all it ever does is it can discard, forward to a neighbor, deliver to an upper layer, buffer, or transform a state. So you have to have those set of operations available. And that's pretty much it. Open problems in networking, well, the biggest problem is that the repeater hardware doesn't really work yet. Large-scale networks have not been really addressed by pretty much anybody up until now. That entanglement swapping that I was talking about, connecting different sections of the network, that all involves a lot of policy sort of operations, and we've done some optimization to that. There's still a good deal more work that needs to be done in larger scale networks. Part of the driving reason behind Bill's quasi-async stuff and Liang's work and Austin's work is to try to eliminate some of these round-trip communications delays required in the classical protocols, particularly for purification. There are also one-way purification protocols that are not as efficient. The goal of all of this is to trade off things in the entire system that are low cost or essentially free in order, and we'll do more of that in order to do less of this, right? It's those kinds of engineering trade-offs. And the single biggest one, like Claire said, is really memory. We want to avoid buffering qubits as much as we possibly can. And that was really Bill's driving reason for creating the quasi-async stuff. And it's really good. Now what I want to see is I want to see that put into a more complete overall end-to-end network architecture using something like the QRNA. There's still probably plenty of other management mechanisms, error management mechanisms we can investigate, and the resource management models as well. And ultimately, hopefully, standardization so that we can build this once rather than 100 times. And thanks to the gang of collaborators. There's a list of some of the papers and some nice photos of KO and the gang, including our annual beach day. That's the group. Let's see. So Lucho's the guy who did much of this simulation work, and Sato did the quantum Dijkstra work on that. Those are the guys who did that. There they are. And Shota did the IPsec. That's Joe Touch up there with a recursive Matryoshka doll as part of his recursive networking stuff. Some of our friends. There's FAM. And this is from our beach day last summer, including the paella that interested Burton. So, and that's pretty much it. Don't forget, information's physical. That's it. Thanks. Questions? Anything additional?
So using these constant depth, there's these, from measurement only techniques, these constant depth teleportation circuits, long distance constant depth teleportation.
Long distance constant depth teleportation? I haven't seen
so
that
there's
term.
circuits you can use that will do in constant depth create a long distance teleportation or long distance entanglement. So it seems like in
Who did that? I haven't seen it.
He was at Harvard. I have the paper in my office. I can show you. It was from like 2009 physicist.
Jake Taylor?
Jake Taylor. Thank you. Yeah.
Jake is
So
really.
he did some of it, but a lot of it was also done in measurement only, in the measurement only community.
I don't recall having seen that particular phrase, but assuming we're talking about the same chunk of work, yeah, that's like the PNAS paper or something, right?
What is it?
For the paper from the Proceedings of the National Academy of Sciences.
This is embedded in the appendix of one of Jake's papers.
Okay.
That was on the archive, but we're using it for our Claire's seen the adder work that Paul Pham, my intern last summer, and I did. And we're using this constant depth teleportation circuit there to do long distance, or I should say constant depth fan out, because that would be analogous in that work. So it seems in this work of networking, constant depth would work.
Well, for fan out, actually, in particular, I mentioned at the beginning, one of the things we would like to see is an overall structure for building and using Bell pairs, GHZ states, W states. So we want, that would fit very well into the overall recursive network architecture.
Yeah, so you can do that.
We need a set of requests. Absolutely, it could be done within this framework. We have not simulated that as part of the specific work we've done. I said earlier that there were some things about the work from that group that I was a little bit dubious about. In particular, well, I guess we're being recorded, but I'll say it anyway. But the single biggest thing that I was dubious about was in one of one of Jake's papers. I think it's this PNAS paper. He was trying to determine what the optimal link length is for their particular architecture, and he tested across a big parameter space and came back and said, 20 kilometers is the best for this. But I really think in that case that the result wound up being driven by the entanglement swapping architecture and not the link level parameters that he thought he was evaluating. So I think the conclusion was more or less predetermined by the way the simulation was set up rather than actually coming out of it. So the hardware architecture they have done is fine. I don't think I buy all of the systems statements that they made about what the best way is to do some of this stuff. But
with the constant depth fan out, the problem is there are a whole load of ways we can do entanglement distribution. The problem is getting it high fidelity.
Right.
If you do a constant depth fan out, if you don't have any way of purifying as you go, you're going to have to start with an incredibly good state.
Yeah.
And as soon as you start sending that through the network, it degrades. So there's, I've not seen anything.
But at least the time delays.
Yeah, the time delay is also actually getting it, because you need to use it at the end. It's not just get a link, because you could do constant depth fan out, get a whole load of these fanned out and then purify right at the end. But then you've got purification messages going from one end of your network to the other.
Yeah, if you're doing this within an integrated system, that whole classical messaging, like if you're wanting to get from one end of your computer to the other, or one end of the chip to the other, it's not a problem. But again, a lot of this winds up being how much does each, when in a real distributed system, how much does each node know when, and how do you guarantee that they're making consistent decisions? Some of this does fall out. Some of it you can kind of define a relatively simple algorithm and say, if all the nodes do exactly this, then it'll work. In other cases, I don't think you can actually eliminate some of the stuff. So yeah, so this is simulation or output from one run of our simulator, and you can see that it's building. So this is one transmitter. This is the second node. This is the third node. And this is the fourth node and the fifth node. And you wind up with sort of gradually building fidelity over the course of these with a whole bunch of this stuff. And you can see that in a system this complex, making those decisions consistently and well is not going to be trivial. Right? So finally here, after all this has been running, we finally have a 2-hop link here. Now this one's waiting on the appearance of another 2-hop entangled pair so that it can actually entangle there somewhere. Lucio did these. Let me show you real quick just the this was still using the single chain simulator that Thaddeus and I wrote several years ago. More recently, Lucio's work was to create the actual network simulator that I showed you, and here's what it actually looks like when it's running. And this is actually built off of Omnet++, which is a standard freely available network simulator package. So it's designed for doing wireless simulations and internet simulations of various sorts. And Lucio wrote plugins for this so that we could actually run large-scale networks on top of Omnet using the simulation protocol. And you can see, Iori's the student who recorded this for me. You can hear him clicking on his keyboard. It's a good thing he wasn't actually talking to his girlfriend or something while he was recording this. But yeah, so Thaddeus's original simulator that did the stuff that I showed you earlier with the quantum Dijkstra stuff includes lots of low-level physical simulation stuff, detecting what the right detector window is. How wide do you make these sorts of things in order to optimize the probability of detecting a high fidelity state, and all of that sort of optimization of the Q-bus link. It also supports things, some of the single photon stuff like the Lucan group's work. So it does the same sort of thing. But then that simulator couldn't do networking, and it was, in terms of adapting the messaging and the protocols for purification and things like that, wound up being really brittle. And so we decided that the right thing to do was to rewrite it in a more networking-oriented simulator. So this one does all of the messaging sorts of stuff. We can support routing protocols. We can support, in theory at least, different purification protocols and all these other sorts of things. It doesn't yet have enough of the bottom level physical parameter implementation in it in this simulator. So we've still got.
Normally just use photonic. Because I was thinking when you were mentioning the memory, topological qubits might be a great memory, but if you can bus between a photonic and a topological qubit, you can store it for your.
Yeah, absolutely. One of the big questions is what's the fidelity of that operation transferring from one to the other, right? If it's less, if you want to use these for QKD, so I said all of these simulations were done to reach an end-to-end fidelity of 0.98, which wound up also being useful as the link layer fidelity. That's good enough for running something like QKD. If you want to do distributed computation, fidelity of 0.98 is not going to be enough. You're going to need 4 nines, 5 nines, 9 nines, or something of fidelity by the time you get to this, if you want to run large-scale distributed computations. And there are a few people who've been investigating moving qubits between physical mechanisms, between an electron spin or the nucleus, like the Lucan group is doing. And most of those, the fidelity looks like it's going to be pretty low, at least for the foreseeable future. And if you want to say, if you're going to store it for a long time, keep it, and then say, after we bring it back out of the memory, then we'll rerun error correction or we'll rerun purification or something, that's fine. But if you think you're going to do it all purification once and then store it in the long-term memory and leave it there, and then use it right afterwards, then that busing protocol has to be extremely high fidelity. And that's going to be a problem. All right. Anything else? Thanks.